Okay, so for the last example here, I want to talk about conservative and non-conservative forces. In particular, I want to look at a non-conservative force to show you that the work isn't the same. So when we're talking about the zipline problem, it's probably fairly obvious that the work would be the same because we found that the work going from here to here is the same as the work coming from here to here. These aren't going to the same spot, but if you were to sort of transport yourself along a rope from this platform down here at 120 feet down to this one, which is also 120 feet down from your original location, transporting yourself over that hand rope would do no physical work, right? You'd be really, really tired, but it wouldn't do any work as far as the physics is concerned because the force is coming down, right? The gravity's coming down, and you're going this way. Since they're perpendicular, they do no work. So obviously, that shows you that at least for those 2 points, that would tell you that for those, at least over that triangle, things look like they're probably conservative. You can't really tell. It's possible for you to choose two. It's possible for you to choose 2 points and 2 paths that have the same amount of work done. So you have to do a little more convincing an argument than that to show that the force is conservative, but we're not going to ask you to show a bunch of random forces that I make up in my head are conservative. That's something for 206. So let's see. We're looking at this other case here, which has friction. Now, friction is something that slows you down. I've already sort of mentioned that it's a non-conservative force. So we're going to see in this case that it's a non-conservative force because you and your friend are going to push boxes from point A to point B. And as you push those boxes from point A to point B, we'll calculate the work for this path, and then we'll calculate the work for this path, which is along a semicircle, which means it has pi r as its length, whereas this one has just 2r. So this is actually pi times 100, or 100 pi meters. So this is 100 pi meters. And of course, if somebody's going to do that, it's going to be you. It's not your friend. Your friend always gets the easy way. You have to do everything the hard way. So now we want to look at how to get that. I mean, it's all going to be calculating the work. So the work is going to be the force times the distance. Now, it's the parallel distance, but frictional forces always go in the opposite direction of the motion. And since it always goes in the opposite direction of the motion, that means, the distance times that force is going to be equal, right? And so your push is also going to be in the opposite direction of that. So everything's going to be perfectly fine. We just have to figure out what the force for you to keep this moving at a constant speed is, which is just the force of friction, right? So that's F equals mu nu, or mu n. And n, if we were to look at our free body diagram, right? So we have your force pushing this way, you have the friction pushing this way, the friction is coupled to that normal force. They're both from the same contact, they're both reactions from the ground, from the pavement, I'm not sure exactly what you're pushing along, sidewalk, whatever, onto the box. And then there's a weight down this way, there's no net force. So this is what your free body diagram should look like. Okay. With a free body diagram like that, we're saying that F and F are the same thing, which is what we're already using, but we have to figure out what's going on with N. Well, according to this, N is just your normal force is equal to your weight, which is equal to mg, right? So we have the coefficient of friction, which we said was, which up here it says is 0.5. I didn't say that. And times the mass of the box, which we can find up here. It's 200 kilograms, and G is just your friendly neighborhood gravitational acceleration. So let's look at this. 0.5. I've been watching the. I haven't been watching, but I didn't see a. Why did I want to look at the old Spider-Man cartoon from the 1970s? I think I saw somebody doing a cover of the. Somebody did a cover of the Spider-Man song. I think it was probably Hillbilly Moon Explosion. I'm not sure. Let's see. So then I was thinking, well, Ralph Bakshi worked on that, I think. So let's go look at that again. And it's just as bad as I remember from being a kid. I mean, it's a Saturday morning cartoon. All right, so let's see. We have 0.5 times 200. That's 100 kilograms times 9.8 meters per second. So 100 times 9.8 is 980. And kilograms times meters per second are newtons. Okay, so that's the force F that we're going to use in this W equals FD equation, this calculation of work. All right, so let's see. What are we going to do? Well, first we'll do the easy one. I mean, they're just as easy. We've already told you how easy they are. Let's see. You've got a friend over here. So we'll calculate for your friend first. That's W is equal to the force times the distance. And the force is 980 newtons times your distance, which is 200 meters. Okay, so 980 times 200. 2 times 98 is 196. 196. And let's see, we have 1, 2, 3 other zeros that I was ignoring, so 196,000 Newton meters. Okay, let's see if I got that right. And I did. Okay, good. Or at least I was wrong in the exact same way twice. One of the two. I either got it right or I was wrong in the same way twice. Both are good enough for now. All right, so let's see. Well, your work is provided by the same equation, right? Because, like I said, your frictional force is always pushing back along that direction, along your direction of the travel. Let's see. You do have to push it a little bit, I guess, in perpendicularly to make it move in that circle, but that doesn't affect the work, remember. The work is only affected by your parallel forces. Okay, so let's see. What was I doing? Oh, so we have 980 newtons is the force that you're pushing with from up here. And then this is your distance. I was just talking about that earlier. The distance is equal to pi over 2 times d, which is 200 meters. So that makes that 100 meters. So that's 980 times 100 times pi. So that's 98,000 times pi. And 98,000 times pi is 3... it's less than that. Oh. See, 307,000 Newton meters. See how I did that? Oops. I forgot a 0. Okay, but they're exactly, but that's the right number. I just didn't type a 0 in that slide. So we have you doing a lot more work than your friend, more than 50% more work than your friend. Probably about 57% more work than your friend, in fact. So that's basically what's going on. To push around the planter is, you know, probably about 50% more work than pushing in the straight line. So you probably should have waited for your friend to finish pushing their box before you started pushing yours. You'll know better next time. All right. So that's enough for now, and I will talk to you pretty soon, at least in my head.